The next family of organic chemicals we're going to look at is the homologous series of the alcohols with a covalent OH group called the hydroxyl group. And what we're going to do, we're going to look at some of the members, we're going to look at alcohols burning, oxidation and different types of oxidation and other alcohol reactions. And here are the first few members of the group. And with the C3 and above, you can have the OH group attached to different carbon atoms, which will make isomers. And so that's why we've labelled those where propan-1-ol has the OH group attached to the first carbon atom. And how can we write a general formula? Think about the other general formulas that you know, particularly the alkanes, because the alcohols here are going to have single bonds between carbon atoms. So what is actually different? So you're adding an OH, but taking one of the hydrogens in the hydrocarbon chain away. So we end up with CN, H2N plus 1, OH as the general formula. And we're going to look at several properties of alcohols: combustion, dehydration, esterification, and oxidation. I'm going to start off with combustion. This one here is where you've got atmospheric oxygen and burning the alcohol, here the equation with ethanol. You can have partial oxidation, and the square bracket O is showing you that you've got an oxidizing agent rather than diatomic oxygen molecules. And it involves heat, but no direct flame, so it isn't combustion. And look at the product, CH3CHO. What homologous series is that? The oxidizing agent can be acidified sodium dichromate, and you have to distill the product to separate it. And this, the product here with this characteristic CHO functional group, is an aldehyde. And to distill the product, you're going to use a regular condenser. The oxidizing agent and the alcohol are in the flask on the left. The reaction takes place and the volatile material will go through the delivery tube and condense in the water jacket. So there we're forming a liquid. This one here is ethanol, but with further oxidation you will get a carboxylic acid functional group, COOH. The one that's written here is ethanoic acid. Now this reaction, again heat but no flame, takes longer. So how do you keep your ethanol and your in contact with your oxidizing agent longer, and the intermediate product of ethanol, which is being oxidized, you have a reflux condenser. The condenser is positioned vertically, so any ethanol that was produced, or indeed any unreacted ethanol that goes vertically up, will condense and run back down to be in contact with the oxidizing agent more. And that's called reflux. And you just have cold water circulating in the jacket around the tube. And we're going to look at the redox equations. Here we have the dichromate going to chromium-3 ions, and if we write the half equation, it's acidified, so you've got hydrogen ions as well, and you need 6 electrons to balance. The oxidation, here I'm just showing the oxidation to ethanol and producing H plus and 2 electrons. So we're going to compare that to the reduction half equation, and you'll see that one has 2 electrons on the right and the other has 6 electrons on the left. So the top equation will have to be multiplied by 3 in order to be able to cancel out the electrons. And at the bottom, 2 equations show that has happened. So you've got 6 electrons in both, and you're then going to cancel those 6 electrons and add the 2 equations. That isn't the final equation, because if you notice, you've got H plus on both sides of the equation, and we just want them on one, obviously the left side, which has more. So you're going to subtract 6H plus from both sides, and then you end up with the reaction, the full equation. And the question is, what do you see? So the original orange sodium dichromate will turn to green chromium 3 compound. And then if we look more closely, if it's a primary alcohol, and that's where the OH is attached to a carbon atom that is attached to one other carbon atom, you get ethanol and ethanoic acid. With a secondary alcohol, so the OH group would be attached to a carbon atom that is attached to 2 other carbon atoms, you're going to end up with a ketone with the characteristic CO group, and here you've got 2 methyl groups attached to it as well. So that would be, with 3 carbon atoms, would be propanone. Tertiary alcohols, so you would have your OH group attached to a carbon atom which itself is attached to 3 other carbon atoms. There is no reaction. And so if you look at what happens with the oxidation, what would you expect the product to do? And it's going to not be happening. So another reaction, the alcohols can be dehydrated, forming an alkene. So really preparation of an alkene as well. So the here showing ethanol producing ethene and water, and you're using aluminum oxide as the dehydrating agent. And 1 propanol will produce propene. So what will happen if you dehydrate 2 propanol? Where would the double bond go? Drawing the structural formula will help. So here's one for the ethanol dehydration. And here's the apparatus. Powdered aluminum oxide, it's sort of in the middle of the test tube, closer to the mouth. That's heated, and a tiny amount of heat is given to the ethanol soaked into mineral wool, because if you heat that strongly, it won't react with cold aluminum oxide. So heat the dehydrating agent first. That doesn't appear in the equation. And so any water that's given off as the product or water vapor would be added to the collecting process on the right, where the ethene is collected by downward displacement of water. And then we've got what you do with the alkene that you've produced, again reviewing what we did with alkenes. Burn some of it, compare the flame, look what happens with bromine and an alkene addition reaction. Oxidation with potassium manganate 4 in 3 and 4, but number 4 is acidified. So That's the reaction that you're looking at. And then we're going to look at esterification. So you've got an alcohol reacting with carboxylic acid, giving the ester. So here, ethanol and ethanoic acid, it's ethyl ethanoate and water. Note that it's reversible, and you need a concentrated sulfuric acid catalyst with this. And the esters have these very characteristic flavors and fragrances. Many of the smaller ones are what we recognize as fruits. So here's another reminder of the oxidation, partial oxidation to ethanol, further oxidation with reflux to ethanoic acid, and you'll use acidified dichromate as your oxidizing agent. So the OH functional group, it's not basic, it's not an ionic hydroxide, it's covalent, and the alcohols are soluble in water, or certainly the ones with the shorter R groups, hydrocarbon groups, are soluble in water.